Hi everyone, I'm Mingfu Liang, a PhD student at Northwestern University, and I'm going to talk about our paper AIDE, an automatic data engine for object detection in autonomous driving. This is a dry work with Jong-Chyi, Samuel Schulter, Sparsh Garg, Shiyu Zhao, Ying, and Manmohan Chandraker. Traditional data engine for autonomous driving in the industry is always trade secrets and rely heavily on extensive human labeling and intervention, making it hard to scale up with anonymous amounts of unlabeled data collected by the autonomous vehicle. Motivated by this challenge, we proposed the first automatic self-improved data engine, short as AIDE, leveraging the recent advancement of vision language models and large language models to automate the data engine for the first time. AIDE consists of 4 components: the issue finder, data feeders, model updaters, and verification, all empowered by a vision language model and a large language model. In the present paper, we consider safety-critical novel object detection task to showcase the effectiveness of the AIDE. Now I will talk about each component of AIDE. First, given an input image, the issue finder will contrast the label predicted by the object detector on hand and a dense description predicted by the dense captioning model, for example, the author. Then the issue finder identifying the objects that is missed in the original label space automatically. The name of the novel object will be passed to the data feeder to construct the test prompt and leverage test-based image retrieval to query relevant image for auto labeling. The queried images are then sent to the model updater. The first step is the auto labeling for the novel object, where we first use zero-shot detection methods like OV2 to generate object proposal, and then we perform zero-shot classification using CLIP. We also pseudo-label the known object using the existing detector on hand. Then we continually train the existing object detector by the pseudo-label of both the novel and known object to mitigate the catastrophic forgetting issue. Finally, in verification, we aim to verify the updated detector with minimum human effort. Due to the vast amount of unlabeled collected data, it's highly expensive for humans to create a specific held-out test set for verification. Therefore, we consider using large language model to generate diverse scene description as test scenarios, and then retrieve images using vision language model from data feeder again. Then, we use the updated model to predict the novel object on those images, and then let human to verify whether the prediction is correct. If it's not, then we can collect the human feedback and then run the data feeders and model updaters to retrain the model again. To verify the effectiveness and scaling law of AIDE, we compare with different learning paradigms, is that open vocabulary object detection, supervised learning, and semi-supervised learning. The figure below shows labeling and training costs versus the performance of the novel categories. The number beside each point represents the labeled images have been used for OBOD, supervised, and semi-supervised learning. For AIDE, the number represents the number of images verified by the human. We find that by verifying a very small amount of images, is that 30, AIDE reduced 56 costs while increasing 2.2% average precision compared to supervised learning with 100 labeled images. Moreover, AIDE also scales by extending images pool for data feeder. The bar chart shown below demonstrates that AIDE scales by adding more unlabeled images from different autonomous driving datasets, which reduced 83% cost while increased 4.6% average precision compared to supervised learning with 100 images. For more technical and experimental details, please scan QR code for more information. Thank you so much for listening.